Hey, so welcome back, and this is another daily code problem. So today it's called Uncrossed Lines, and it's a dynamic programming problem. So I'm going to give you the memoization approach. You can do kind of the tabulation or the bottom-up approach, but I'll just keep it simple. I'm learning this pattern myself, so yeah, let's go ahead and do it. So essentially, what this is a very kind of a clever way of rewriting a famous dynamic programming problem called a longest common subsequence, like so, also known as LCS. And so basically, all that you want to do for this question, I just mainly ignored the description because it wasn't really explained very well, is that you're given two arrays and they kind of sit on top of each other, and you want to pass lines between the two where the numbers match. And so that's basically it. Like the thing that you have to keep in mind is that these numbers can't cross. So you want to return the maximum number of these lines that you can connect, but you can't connect 2 and 2 here because that would overlap with this line. And so, and you obviously want to use this one because it's not going to cross anything. So you could either make this line through there or the one that they're already doing, and that's it. So the max would be 2 in this case. And then, yeah, you can draw out these if you really want to, but that's it. So the reason why this is like a longest common subsequence problem is, well, naturally we want the longest number, so that's the longest part. And then common subsequence is that, in this case, this is a common subsequence between these two arrays, because you can kind of view this as 1, 4 on the top, but then also 1, 4 on the bottom, since we're both just ignoring these 2's. You could also get the common subsequence of 1, 2, if you want to choose this one and this one, and this one, this one. Like the order is being maintained for both of them, since 2 follows 1. Okay, and so to do this, once again, we're going to do the memoization approach, which is basically recursion with caching so you don't do all the repeated work. So just to show you the recursive relationship that we're building is basically you would start off with 0, 0. And that's saying you're going to start at index 0 on the top and then index 0 on the bottom. And then you can branch off this. And there's really only one branch from here, because in this case, we know that whenever the numbers at these 2 pointers are the same, we want to increment them. And in this case, since they're at the same position, we just want to increment them both. Okay, so then we just move down to 1, 1. Since we can only, we have to move them both because we can't reuse a number after we've used it. So now that we're at the next step, oh, I didn't want to delete that. So 0, 0, then we're at 1, 1. So now we're pointing at these two. And now we have 2 paths that we can go down. Since they don't match each other, you can either go down a 1, 2 by incrementing the bottom pointer, or you can go 2, 1 by incrementing the top pointer up a level. Okay, and so this is where you start branching off, and you kind of need the maximum of these 2 different paths. Okay, and so to do that, then you would have to go down this route with like 2, 2 or 1, 3. And the same thing for this path as well. Okay, and so the problem with this is you can see that there's a lot of repeated work. This might be more recognizable once you see that, okay, this goes down 2, 2, or it can go down 3, 1. And so this path here is being repeated. Okay, and so we want to make use of this recursion, because otherwise, or this repeated work, or otherwise, you would get actually 2 to the exponent of m plus n time complexity. And it's 2 because you're making 2 decisions at every level. That's how we get that exponential relationship. And then m plus n is because, well, we're considering the worst case, And in the worst case is you're only going to be moving one pointer for one of these arrays at a time. And so that'll just be like 1, 2, like 3, 4, 5, then 6. Okay, so it's to the exponent of m plus n. But by doing this recursion and caching or using the memoization, we can bring this time complexity down to just m by n. But it comes at the trade-off of also using m by n like space as well. So this is like the space complexity, and then this is the time complexity. But this is much more favorable than having a 2 to the n plus n time complexity with constant space. Okay, so let's go ahead and implement this recursive relationship, and then I'll show you how we can implement memoization. So the first thing is we're going to want to return the result of this depth first search function, and we start at that beginning index of 0, 0. So we start at pointing at these two numbers, and let's go ahead and define that function. And we'll just say like I and j as the pointers. And so our base case will be when these kind of overstep and cross over the length of our array. And so once that happens, we'll just want to return 0 as like that base case. And so if I is equal to the length of the first array, or j is equal to the length of the second array, then let's just return 0. This is like our base case. Okay, and so from here, what we're going to want to do is consider those two different paths. The first path, and I'll just call this path 1, and with one branch, is just the case where, okay, if the number at I and j, that cross, if I and j are the same, then we're just going to be pointing directly at each other here. Okay, so we want to always use it. It's kind of a greedy way that way, where let's just use that value and then increment them. Okay, and so that is if I is equal to, or if the number at I is equal to the number at j, then let's go ahead and return 1 plus incrementing this by both of them by 1, since we can't reuse these values. So I plus 1 and j plus 1. Okay, and we want to be using nums1 and nums2 here. Great, so I hope that's fairly intuitive. And from here, we just kind of move them both up by 1, but we also want to consider the second path here, path 2, and that is if our number at 1, or wait, let's see here. We just want to say else, because we have to be doing one or the other. So in this case, they don't match, and so then we know that, okay, we want to return the maximum of these two different paths. So we could either go down, that was when it's like, okay, because these two values don't match, we can either increment this pointer by 1, or we could increment the other one by 1. Okay, and so to do that, let's just go down either of these two paths. So it could be this, or it could be incrementing j by 1. Okay, and so from here, the last thing that we're going to want to do is just return the result that we're at. So because we're going to do memoization, I'll just go ahead and create our DP hash map. You can also use a 2D array, but I find this one just more intuitive. And so we would just want to say, okay, let's return DP at I comma j. Great. Okay, and so from here, what we're going to want to do is we have to see if this evaluation is like in our recursive function. And so in that case, I just realized here, we don't want to return this. We would want to return this case, but in this case, because we're going down the two different paths, let's just say, okay, dp at I comma j goes here. And this is how we actually do that memoization. Great, that makes more sense now. And then same thing here. Okay, so we're gonna store this temporarily in our hash map as kind of a lookup, and then we just take the maximum of these two different paths. And now we could just be like returning this and not doing that, but this enables us to, at the beginning, check if I comma j has already been like pre-computed in this hash map. Then let's just return dp at ij. Let's try running that. Looks good. Submit it. And success. So yeah, let's just go through this one more time. So basically, base case is when they go out of bounds. So that is just saying, okay, that doesn't give us any extra addition or number of connecting lines. So let's just return 0. We don't want to add anything. And then from here, if this step has already been pre-computed, then let's just return what we already computed there. So that's caching the repeated work. But it comes at the trade-off of additional space complexity. And then here's kind of the core logic of the algorithm. There's two different paths. One is, okay, if these equal each other, then let's just both increment those 2 pointers because, well, they're the same and we want to not be able to reuse them. And then otherwise, we'll have to go down this path where we'll recursively be calling it on moving the top pointer by 1, or we can call this function again by incrementing the bottom pointer by 1. And you just want to take the maximum of those 2 outputs and then store it in this step so that it can be checked again as pre-computed work. And then finally, because this result gets stored in this lookup table, you're just then going to return it. And yeah, so that's the algorithm, and I hope it helped a little bit. So once again, it's n by n time complexity and also space complexity because this is like a 2-dimensional array. It's just simpler with a hash map. But yeah, once again, I hope it helped, and good luck with the rest of your algorithms. Thanks for watching.